Bismillahirrahmanirrahim. Assalamu alaikum, students. So let us start today's topic. Our today's topic is superposed vibrations of different frequency. In bracket, I write idea of beats. So in this lecture, we are going to consider two vibrations, two simple harmonic motions, which have different frequency, and find their superposition. That is, we superpose them and find the resultant motion. In the last lecture, let me refresh your memory. In the last lecture, we discussed the superposition of two SHMs of equal frequency. One SHM was written as x1 equal to a1 cos omega t plus alpha 1. The second SHM was written as x2 equal to a2 cos omega t plus alpha 2. So we considered superposition of these SHMs. They had different amplitudes A1 and A2, but the frequency omega was same, right? But in today's lecture, the frequency of SHMs we take to superimpose is different. So suppose we have two vibrations of different amplitudes A1, A2, and also of different angular frequencies omega 1, omega 2. Now, in the last lecture, the phase difference of these two SHMs is just alpha 2 minus alpha 1 is the phase of one SHM, is the phase of second SHM. So if you find the difference omega t plus alpha 2 minus omega t minus alpha 1, omega t will cancel out. You will get alpha 2 minus alpha 1. So in that last lecture, in the case of equal frequencies, the phase difference between the superposing SHMs is alpha 2 minus alpha 1, which is constant in time, right? But in this case, different frequency case, in contrast to the last lecture situation, the phase difference between the vibrations is continually changing. So let me write it. So in this case, the phase difference between the vibrations is continually changing with time, right? So this is the difference between equal frequency case and different frequency case. In equal frequency case, the phase difference between the vibrations is constant in time. Here, the phase difference between the vibrations is continually changing with time. So this has consequences. Now, the specification of some initial non-zero phase difference is in general not of major significance in this different frequency case. So to simplify the mathematics, let us suppose therefore that the individual vibrations have zero initial phase and hence can be written as follows. X1 equal to A1 cos omega 1t, X2 equal to A2 cos omega 2t. So this is our first SHM. This is our second SHM. You can see amplitudes are different, frequencies are different, omega 1 and omega 2. And at t is equal to 0, the phase of both the SHMs is 0. Where at t is equal to 0, this angle will become 0. Omega 1t is 0, omega 2t is 0. Now, at some arbitrary instant, the combined displacement will then be as shown. OX in figure 1. Let me draw the figure first. So let me take this color. Let this be point. Let me make it clear. Let this be point 2. Let me draw the figure first, then I will explain it. This angle is 1t. This angle is omega 2t, and let this point be P. We join this OP. This projection, let there be this capital X. Let this be small x. This is my figure 1. You can see in this figure 1, we have represented the two SHMs by rotating vectors. This first vector having length A1 and making angle omega T1T with the x-axis represents first SHM. You can see its projection on x-axis represents x1, because x1 is A1 cos omega 1t, right? And then the second vector with length A2 making omega 2t angle with x-axis, this angle here, and the angle made by this vector with the x-axis will be same, represent the second SHM, right? So its projection, that is this length, is just x2, where x2 is A2 cos omega 2t, right? Now the resultant OP vector will represent the amplitude of the combined motion, and its projection represents the total displacement x. This OX is the projection of OP, and this represents x, the displacement of the resultant SHM, right? Now, in this case, as these vectors rotate, as we already said, that the phase difference between this A1 and A2 vector will change with time. So this cannot be thought of as rotating. This triangle cannot be thought of rotating bodily with time, because the phase difference between first vector and second vector will change with time, unlike the equal frequency case, which we discussed in the last lecture, right? So let's move. Now the length OP of the combined vector, the length OP of the combined vector must always lie somewhere between the sum and the difference of A1 and A2. I'm saying the length OP of the combined vector, that is this OP, must always lie somewhere between the sum and the difference of A1 and A2. As these vectors rotate, phase difference keeps on changing, so the length of OP vector will keep on changing, but always it will lie between the sum and the difference of A1 and A2. Think about this at home and convince yourself. Think about it. Right? Now the magnitude of the displacement OX is OX, projection of OP on x-axis, will also change with time. So the magnitude of the displacement OX itself may be anywhere between 0 and A1 plus A2, right? Now, unless there is some simple relation between omega 1 and omega 2, this omega 1 and omega 2, the resultant displacement OX will be a complicated function of time because of this changing phase difference with time, right? Now, the condition for any sort of true periodicity in the combined motion is that the periods of the component motions be commensurable. So let me write. So in general, I am saying this resultant displacement will be a complicated function of time, but the condition, let me write it, the condition for any sort of true periodicity in the combined motion is that the periods of the component motions, that is first SHM and second SHM, be commensurable. That is, there exist two integers n1 and n2 such that t, period of the resultant motion, is n1 times t1. T1 represents the period of first SHM, is n2 times t2. T2 represents the period of the second SHM. So when this condition is satisfied, we say the periods of the component motions are commensurable. And this is the condition for the resultant displacement being periodic in nature, right? Then the period of the combined motion, that is the value of t as obtained from this, let me name it equation first, using the smallest integral values of n1 and n2 for which the relation can be written, right? I repeat, I am saying in general, the resultant displacement will be complicated function of time, but if this condition is satisfied that there exist two integers n1 and n2 such that we can write the periods of component motions t1, t2 this way, then there will exist some sort of true periodicity in the combined motion, right? Now, if the two SHMs, let me use some other color, if the two SHMs are quite close in frequency, that means this condition is satisfied. Now the component motions are commensurable, so there is periodicity in the resultant displacement. Now, and in addition to this thing, the SHMs are quite close in frequency. Then what happens? The combined disturbance exhibits what are called write it in some other color, beats. I repeat, if the two SHMs are quite close in frequency, that means omega 1 and omega 2 are close. The combined disturbance exhibits what are called beats, right? Now this phenomenon of beats can be described as one in which the combined vibration is basically a disturbance having a frequency equal to the average of the two combining frequencies, but with an amplitude that varies periodically with time. I hope you know the idea of beats. I still repeat and write it for you. This phenomenon here, or let me write the phenomenon of beats can be described as one in which the combined vibration is basically a disturbance having a frequency equal to the average of the two combining frequencies, but with an amplitude that varies periodically with time. This is what is called the phenomenon of beats. We combine two SHMs, omega 1, omega 2 are close. We get a resultant vibration, resultant SHM, which has frequency equal to the average of the two combining frequencies, but has amplitude that varies periodically with time. Now, the beating effect is most easily analyzed if we consider the addition of two SHMs of equal amplitude, right? So let us do that. So we write x1 equal to a cos omega 1t, x2 equal to a cos omega 2t. So we are considering the addition of two SHMs with equal amplitude. Omega 1 frequencies are different, but amplitude is same in order to understand the beating effect. Now, by addition, we get x is x1 plus x2. When you do that, we get this 2a cos omega 1 minus omega 2 over 2 times t. Let me use another color here. Cos omega 1 plus omega 2 over 2 times t. Let me encircle it. This is important. Where I have used this trigonometric identity, let me specify that using cos alpha plus cos beta equal to twice cos alpha plus beta over 2 times cos alpha minus beta over 2. I'm saying by addition we get resultant displacement x is x1 plus x2. We substitute for x1 a cos omega 1t, for x2 we substitute a cos omega 2t. Then we use this formula. You can take a common. Then we use cos alpha plus cos beta is equal to twice cos alpha plus beta by 2 times the cos alpha minus beta by 2. When we do that, we get our result as 2a cos omega 1 minus omega 2 over 2 times t, and cos of omega 1 plus omega 2 over 2 times t. Check this at home. This is your assignment. Check at home. You have to simply use this trigonometric identity to arrive at this result. So let me name it second. This is my second equation. Now, clearly, this addition, when we add x1 and x2 to get the equation second for the resultant displacement, this addition as a purely mathematical result can be carried out for any values of omega 1 and omega 2. But its description as a beat phenomenon is physically meaningful only if mod omega 1 minus omega 2, let me write it, you will then understand it. I'm saying this addition, right? Which addition? Of x1 and x2 as a purely, I'm writing it because it is important, you may note it, mathematical result can be carried out for any values of omega 1 and omega 2. There is no restriction for that. You can mathematically add x1 and x2 to get this x for any values of omega 1 and omega 2, right? But its description as a beat phenomenon, when we describe it as a beat phenomenon, is physically meaningful only if mod of omega 1 minus omega 2 is much less than omega 1 plus omega 2. That is, if over some substantial number of cycles, the vibration approximates to sinusoidal vibration with constant amplitude and with angular frequency omega 1 plus omega 2 over 2. I repeat it, I'm saying This addition can be done as a mathematical result for any values of omega 1 and omega 2. But when we give its description as a beat phenomenon, to make it physically meaningful, that description, that is only possible when mod omega 1 minus omega 2. That means whether omega 1 is greater than an omega 2 or omega 2 is greater than omega 1, we take mod, magnitude of the difference between the frequencies. It must be much, much less than omega 1 plus omega 2. Then we can describe it in terms of beat phenomenon. That physically means that over substantial number of cycles, the resultant vibration which we get approximates to sinusoidal vibration with constant amplitude and with angular frequency omega 1 plus omega 2 over 2. You can see the resultant displacement which we got has frequency omega 1 plus omega 2 by 2, and this thing is its amplitude, which is changing with time periodically because it contains the cos, right? Now you can see the combined displacement write it. The combined displacement can be fitted within an envelope defined by the pair of equations x equals plus minus 2a cos omega 1 minus omega 2 over 2 times t, because the rapidly oscillating factor in equation second that is cos omega 1 plus omega 2 by 2t always lies between the limits plus minus 1 and equation, let me name it third, this is my third, and the equation third describes a relatively slow amplitude modulation of this oscillation. Try to understand it. This is our equation second. This is the amplitude which periodically changes with time, and this factor is slowly changing. because omega 1 minus omega 2 is small compared to omega 1 plus omega 2. This factor, omega cos of omega 1 plus omega 2 over 2t, this factor is rapidly changing. Amplitude is slowly changing because the frequency here is difference, here is sound. So that's what I said. I said the combiner displacement can be fitted with an envelope defined by the pair of equations. When the rapidly oscillating factor, that is cos omega 1 plus omega 2, it will always lie between plus 1 and minus 1. So the displacement will then become plus minus 2a cos omega 1 minus omega 2 over 2 times t. This will lie between plus 1 and minus 1. So we can fit the combiner displacement within an envelope defined by these equations, right? And this equation third, that is this equation, describes a relatively slow amplitude modulation of this oscillation, right? So this is the idea of beats. So what happens? I will show it roughly, not to scale. We have two sinusoidal oscillations. They have, I'm telling you, I'm showing it roughly. They have, let it be omega 1, this be omega 2. We combine them. I'm showing this displacement in time approximately. And what happens? We get this type of situation. Let me show it some other color. It's all rough. You can see it in the textbook. This is this slowly changing factor. That is this factor, amplitude factor, right? And inside it, there is rapidly moving, rapidly changing oscillation. So see what happens when these two oscillations combine. We get the resultant vibration whose frequency is changing rapidly, omega 1 plus omega 2 by 2, but whose amplitude is changing slowly. Amplitude of the resultant vibration is changing slowly, and this envelope defines that slowly changing factor. But the vibration itself is fast, its frequency is arithmetic mean of omega 1 and omega 2, right? So you can see a maximum in the amplitude of the, let me use another color, a maximum in the amplitude of the resultant vibration is, let me write it, is detected whenever cos this factor omega 1 minus omega 2 by 2t becomes plus minus 1. I repeat, a maximum in the amplitude of the resultant vibration is detected whenever this cos omega 1 minus omega 2 over 2t is plus minus 1. Let us go to the equation second. When this, let me use some other color, when this factor, this whole thing is amplitude, when this factor becomes plus 1 or minus 1, what will happen to the amplitude? It will either become plus 2a or minus 2a. Those two values are its maximum values, right? Hence, there are two maxima in each period of the envelope wave, right? Hence, there are two maxima in each period of the envelope wave. I repeat, the cycle of envelope wave is decided by this factor. Envelope wave means the wave representing the amplitude variation, right? Now, it has cycle, it has frequency. Now, in its each cycle or period, amplitude goes maximum twice. Whenever this factor becomes plus 1 and minus 1, amplitude goes plus 2a and minus 2a, right? So we said there are two maxima in each period of the envelope wave. Now, because the amplitude varies with the frequency, what is the frequency? Omega 1 minus omega 2 by 2. The number of beats per second or beat frequency is twice this value. I write omega beat is mod of omega 1 minus omega 2. This is important. I repeat, I'm saying maximum in the amplitude of the resultant vibration is detected whenever this factor becomes plus minus 1. Hence, there are two maxima in each period of the envelope wave. Because the amplitude varies, as you can see, with the frequency omega 1 minus omega 2 by 2, the beat frequency will be double of that. So the number of beats per second, which is beat frequency, omega beat, is twice this frequency, that is twice omega 1 minus omega 2 by 2, which is omega 1 minus omega 2, right? So beat frequency means the number of beats per second. right? So you can see beat is the maximum of amplitude. Beat is the maximum of amplitude. Now, in each cycle of the amplitude becomes maximum twice. That's why beat frequency is 2 times the frequency of the amplitude, which is omega 1 minus omega 2 by 2. So it's omega 1 minus omega 2. We have written it in modulus. Whether omega 1 is greater than omega 2 or omega 2 is greater than omega 1, we have to take the difference. So number of beats per second, this is actually, we are talking in terms of angular frequency. If we talk in terms of the number of beats per second, it is actually angular beat frequency. Then you talk of new beat. I should write it, nu 1 minus nu 2. You know omega is 2 pi nu. So omega beat is actually 2 pi nu beat, right? Omega 1 is 2 pi nu 1 and omega 2 is 2 pi nu 2. So number of beats per second is actually nu beat. This is angular beat frequency. Let me write it. This is angular beat frequency. Number of beats per second or beat frequency is nu beat. I hope it is clear to you. So if one tuning fork vibrates at 438 hertz and second one vibrates at 442 hertz, right? Then the resultant sound wave of the combination has a frequency of 440 hertz. And beat frequency is 4 hertz. Let me explain. I'm saying if one tuning fork, so this is one tuning fork vibrating. So it's my, let it be my omega 1. So one tuning fork, if it vibrates at this frequency 438 hertz, right? And second tuning fork is vibrating at 442 hertz. So this is my omega 2, right? Now the resultant sound wave, this is my resultant sound wave. Resultant sound wave vibrating of the combination, right? Let me write it of the combination. Resultant sound wave of the combination, it has frequency of 440 hertz and beat frequency is 4 hertz. How do I know it? One tuning fork is vibrating 438 hertz, second is 442 hertz. So the difference between them is 442 minus 38 is 4 hertz. So beat frequency is their difference as we established it. But the resultant sound wave will have a frequency of their arithmetic mean. It will be 442 plus 438 by 2, which is their midpoint, which is 440, right? Which is 440. Because we said that when two waves combine, the resultant vibration will have frequency omega 1 plus omega 2 by 2. but the beats will be decided by when the amplitude becomes maximum. That becomes twice in one cycle of amplitude wave, right? So that's why we said when two tuning forks vibrate at these two frequencies, we will listen to a sound wave of frequency 440 hertz, and we will listen to the beats with beat frequency of 4 hertz. That means we will listen per second 4 beats, right? I hope it is clear to you. This is all for today. Let me summarize the lecture. So in the start, we said we will discuss superposition of two SHMs with different frequencies. Then we refer to the last lecture. We said in equal frequency case, the phase difference is constant in time. But in this case, the phase difference between the vibrations changes with time. That has consequences. What consequences? We said then we gave the rotating vector representation of the situation. We said this OP vector will change with time, but it will lie between the sum and difference of A1 and A2, and the resultant displacement will lie between 0 and A1 plus A2. Then we said in general, the combined oscillation will be complicated, but if this first condition is satisfied, then the combined displacement will be periodic. And if the SHMs are in close frequency, then there is beating effect. We said in phenomenon of beats, what happens to vibrations close in frequency, they combine, they superpose, and we get a vibration having frequency equal to the average of the two combining frequencies, but the amplitude varies periodically with time. Then to understand this beating effect, we consider the case of equal amplitudes. Then we added these two oscillations, we got the beating effect. I gave you homework. Then we discussed how the beat frequency is the difference of the individual frequencies, and we give the example of tuning forks. So I hope you have enjoyed this lecture. Go through all the lectures, prepare your exams, and don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.